This video is going to cover two topics, Pascal's principle and buoyancy. So the first part covers Pascal's principle. Now, you only need to write the part that's in red, that's most important, but if you'd like to write the whole thing for it to make sense to you later, that's fine too. Now, Pascal's principle states that the pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and to the walls of the container. Again, that fluids are not just talking about liquids, but also gases. So you can think of a bike tire. If you're pumping air into a tire, that air is entering the tire and it's increasing the pressure that the tire experiences. Now this pressure is going to be the same at all points inside of the tire. So Pascal's principle is actually applied to a hydraulic lift. Now what a hydraulic lift is, it's a closed container with a small area on one side and a large area on the other side. Now, remember that pressure is force over area. So if we have a force applied to one area, then we create a pressure. Well, Pascal's principle says if this is a closed container, then on the other side, we're also going to have the same increase in pressure. But because our area will be much larger, our force also has to be much greater in order for it to compensate and still produce the same pressure. So you can think of the fraction 8 over 2, where 8 is my force and 2 is my area. This is going to produce a pressure of 4 pascals. Now, if the other side has an area of 4 meters squared, then our force applied, or the force created, also has to increase. And this will increase to 16. Now, if you notice, they both still create that 4 pascals of pressure. This hydraulic system lets a mechanic apply a force that's much less than the force of a car and still be able to lift it. So this first example is pretty straightforward. It says a small piston of a hydraulic lift has an area of 0.2 meters squared. A car weighing 12,000 newtons sits on a rack mounted on a large piston. The large piston has an area of 0.9 meters squared. How much force must be applied to the small piston to support the car? So again, we have force applied over the area applied to is equal to the force that we have to support over the area in which that force is being applied. In this case, this would be the car. This is the force that we are going to apply. I'll put S. So what you're trying to solve for is a force that you're trying to apply. So this is simply F1 is equal to F2 times A1 over A2. Now I think the hardest part in this section is just keeping your numbers straight and being consistent. So our force will be 12,000. Our area will be 0.2 meters squared. And then the area it's being applied over will be 0.9. Again, this is the area of the piston that the car is actually sitting on. Altogether, you get a value of 2,667 newtons. Our second topic is buoyancy. So let's look at an object submerged in a fluid. We know that at the top of this, the pressure is not going to be that great. So we have a pressure is equal to a force over the area. Now this force is being applied by the water above, or this fluid above this object. And we know as we go deeper, the pressure will increase. But since the area does not increase, then the force must. Now this force is coming from the bottom part of the fluid, and it's pushing up. So buoyancy is caused by the difference in pressure at the top and bottom of a submerged object. So this means we're actually going to have a sum of the force going up. So buoyancy is this force, and it is always directed upwards, and it is equal to F equals rho G times volume. Now you don't need to write this equation down because we're going to see a different version of it in just a second. Now we said buoyancy acts on an object no matter the fluid. Now you might say that if we are calling gas a fluid, then shouldn't we feel buoyancy in air? Well, actually we do, but this is so small that we can actually ignore it for the most part. The exceptions are balloons and blimps. So if an object floats in the air, this is where you are going to include buoyancy from the air. So when you place an object in a liquid or fluid, this object is going to submerge a bit. So in order for you to find the force of buoyancy pushing up on your object, you're going to need to know the density of the fluid and the amount or volume of the fluid displaced. So this is the version of the equation I would like you to write down. Now to figure out how much volume has been displaced, you want to find out how much of the object is actually inside of my fluid. That amount is going to be the amount of volume that has been displaced. That's what had to get out of the way in order to make room. Since buoyancy is a force, we're going to have to start off by drawing free body diagrams. Now, I'm going to be setting up a lot of problems. You don't have to write everything down. Write what you think is necessary. So this object is a mass m, is floating on the surface of a liquid. So on that object, I have a buoyant force keeping it floating there. And I have a force of gravity acting downwards. So if I know that that buoyant force is upwards, force of gravity is downwards, then I know that they also have to be equal to each other. So my buoyant force, Fb, is going to be equal to my mass times gravity. So always start off the problem by drawing your free body diagram, then writing the sum of the forces. Then depending on what information you're solving for, you can go from there. Now remember, our volume here is only going to be the volume of the amount of objects submerged. So it would only be this amount of volume. Now we have an object that is completely submerged, but is still neutrally buoyant. Again, we still have our object with a acting on it, and we have a force of gravity acting downward. Because, again, it's just floating there, we have our buoyant force, which is rho g v, is still equal to mass times gravity. But now we have a greater volume submerged than before, so our volume is now different. In this example, we have a mass m is submerged in a liquid. It is released from rest and initially accelerates downward against the resistance of water. So now we're talking about movement here. So, and not only movement, but acceleration. As always, mass times gravity pulling it downwards. Our buoyant force is pushing it upwards. But now we also have a resistance because of that water. You can think of friction. So we'll call this force R because it's a resistive force. And I know it's pointing up because we are accelerating downward. So if we're accelerating downward, just like in free body diagram problems or Newton's laws problems, this is going to be a positive direction. So we'll have mg minus our buoyant force, which is mu, rho g v, again, volume submerged, minus F R equal to MA because it's accelerating. Now, again, we're just setting up the problem here. You would need to have enough information to be able to solve for any one of these variables. In this problem, you have a mass m is submerged in a liquid. It is released from rest and initially accelerates upward against the resistance of water. Again, now we're accelerating the opposite direction. Gravity still acts downward. Now our buoyant force is actually enough to get it to accelerate upwards. And now, because we're accelerating upwards, our direction of friction, or resistance, is in the opposite direction. So, if upwards is now positive, we have our buoyant force, which is rho g phi minus mg minus our resistive force equal to mass times acceleration because we are accelerating. Here we have a mass m is submerged in a liquid and sitting on the bottom. Now, don't forget that because we are actually at the bottom. You do still have your force of gravity acting on it. Now you have a buoyant force pushing up, but you also have a normal force being provided by the surface or the bottom of this container. Because it is just sitting there, that means our normal force plus our buoyant force is going to be equal to gravity. Or if you'd like the sum of the forces the way we normally write them, it would look like this. So remember that our normal force plus our buoyant force, which is rho g v, is equal to mass times gravity. In this example, we have a mass m is submerged in a liquid and suspended by a string. Again, force of gravity acting downwards, tension acting up, and also a buoyant force acting up. If it's just being suspended, that means our tension plus our buoyant force minus gravity is going to be equal to 0, or that our tension together with our buoyant force is going to be equal to mass times gravity. In this example, we have a mass m is submerged in a liquid and suspended by a spring. Again, object, force of gravity, buoyant force up. If it's just being suspended, that means our force of a spring, and we know it's upward because it's always against the direction of displacement, plus our buoyant force, which is rho g v, is equal to mg. Again, suspended. Now this example does a little bit more calculations. It says an 80 kilogram mass floats with a portion of the mass sticking above the surface of the water. Determine the volume submerged. Now, again, we know it's sitting at the top. So our buoyant force is going to be equal to our mass times gravity. So rho g v is equal to mg. Now remember that if we are talking about water in this case, our density of water is simply 1,000, and we already know gravity, so we can actually determine what our volume is. So our volume will be equal to mass times gravity divided by density times gravity, or just mass divided by density, which is 80 kilograms divided by 1,000. So 0.08 meters cubed, our unit for volume.